Cool. So I'll start the second half of my talk. Uh, right. So there's when we're in almost Fuchsian space, when like the maximum principal lambda, when the maximum principal curvature lambda naught is less than one, then we have this really nice picture like what's happening in the geometry. There's one minimal surface in the middle, and we have these like mean convex foliations on both sides. And we can write down the metric explicitly, and so that what that does, it lets us um, it lets us estimate so the volume of the convex core and like all these like how there's dimensional limit set in terms of lambda naught, like in terms of the maximum principal curvature. Um, but what happens is that as lambda naught tends to one, the estimates blow up. So we kind of lose control as lambda naught tends to one, just through this naive approach of just explicitly writing down the metric and kind of going from there. So yeah, so then kind of the question here is that we originally kind of like what was sort of our starting point was what happens when the maximum principal curvature is equal to one. So say someone hands you just a hyperbolic structure on M that where M is homeomorphic to a surface times R, and then if there's happens to be some minimal surface in there with principal curvatures less than or equal to one, with principal curvatures equal to one somewhere, right? So not like Uhlenbeck's results are for like when it's strictly less than one, but for here we have some minimal surface with principal curvatures equal to one somewhere. Then the question is like what happens then? Like are you still quasi-Fuchsian, right? Like as we kind of like go to the boundary of the almost Fuchsian space, like can it degenerate or like what's going on there? Yeah, and so we answer this question. So we I guess building on things that Andrew Sanders had done, which are kind of in this direction, and we used a lot of his ideas for what we do. Definitely, we were able to show that if the maximum principal curvature is equal to one, lambda naught's equal to one, then the manifold has to actually be quasi-Fuchsian, right? Um, yeah, and so being quasi-Fuchsian, it's sort of the same as being quasi-asymmetric to just like a Fuchsian manifold. That's another way to define being quasi-Fuchsian is there's some quasi-isometry from a Fuchsian manifold to uh, your quasi-Fuchsian manifold. And and so for kind of Uhlenbeck's result, where she if lambda naught is less than one, she shows that you have to be quasi-Fuchsian. She kind of like explicitly constructs what the quasi-isometry is, right? And so you kind of know exactly what the quasi-isometry constant is, but it blows up as you lambda naught tends to one, right? But our results kind of the way that's shown is it's a more indirect argument where we aren't actually able to control the quasi-isometry constant, and yeah, since kind of proceeding directly doesn't, like how Uhlenbeck did, doesn't seem to work when the maximum principal curvature is equal to one, right? And so I can't really say that much about how that's proved, but I just want to mention two of the things that go into it because I didn't really know about them before I started working on this, and they're kind of cool. So there's this Kobe 1/4 theorem that you maybe learned in a complex analysis class. So what that says is if you have an injective holomorphic map from the unit disk to the complex plane that sends the origin to the origin, then what the Kobe 1/4 theorem says is that its image is some open subset of the complex plane that contains the origin, and the Kobe 1/4 theorem says that its image has to actually contain a disk of radius 1/4 centered at the origin, right? So it's strong restriction on the kind of like univalent maps. They have to uh, from the unit disk have to uh, their image has to contain the disk of radius 1/4 centered at the origin if they map the origin to the origin. Yeah, and so it turns out that there is a version of this theorem for k quasi-conformal maps where there's kind of the same statement where instead of looking at a holomorphic map, you would look at a k quasi-conformal map from the unit disk to the complex plane, sending the origin to the origin. And then there's an analogous conclusion where you know that the image has to contain some open disk centered at the origin of radius depending on k, but there's some universal radius just depending on k, so that any k quasi-conformal map has to um, contain contain an open disk at the origin of that radius. And so just to say how this kind of end result proof is, it's what we do is we look at the normal exponential map for our surface. We actually lift the universal cover. Okay, and so we kind of have this map from our lifted minimal surface in the universal cover to the boundary at infinity just by kind of like shooting out normal geodesics, right? So we get, this map, from the universal cover of our surface, which is a disk, to the boundary at infinity. And so we're able to estimate the quasi-conformal constant at some points for this normal exponential map. And so we're able to kind of control it, say that its image has to contain some disk of a definite radius. And this lets us get kind of control on what's happening in the universal cover. And we're kind of able to bootstrap off that to get what we want. And then kind of to sort of finish the argument, we use this classification of Kleinian surface groups. So essentially just kind of all the different hyperbolic structures you can have on a surface times R, or complete hyperbolic structures on a surface times R, which Bonha did. So either what his result is, I guess, either you're quasi-Fuchsian, you're singly degenerate, or you're doubly degenerate. So just kind of simple description of the possible things you can have happen. And I guess it's kind of an ancestor of the ending lamination theorem, although it's long before that. But I maybe shouldn't have said classification of Kleinian surface groups, because there's just like there are these like stronger results with like the kind of ending lamination that says that you have this data and then kind of this lamination at infinity that tells you what the whole hyperbolic structure is. But I just mean kind of in this like Bonha theorem sense of like you have this trichotomy. So maybe I shouldn't have said classification here, but anyways. But yeah, cool. So anyway, so with this theorem in hand, define the weakly almost Fuchsian space to be just space of all hyperbolic structures where there's some minimal surface in the middle that has principal curvatures less than or equal to 1. And so by our theorem, we know that these all have to be quasi-Fuchsian. Okay. Right. And so now we kind of we're kind of in a position to answer like this question kind of handle this difficulty that you have where like your estimates sort of blow up as the maximum principal curvature tends to 1. So we kind of the way that we're going to handle that is to work with this weakly almost Fuchsian space. Right. And so we kind of do the same kind of run the same scheme as like what Uhlenbeck did in parameterizing almost Fuchsian space by pairs of conformal structures and holomorphic quadratic differentials, right? And so what we do is we construct this compactification of weakly almost Fuchsian space it extends the Deligne-Mumford compactification. So basically, if you forget the holomorphic quadratic differential, it's just the Deligne-Mumford compactification. But then we have this holomorphic quadratic differential that's telling us how our minimal surface is sitting inside the ambient hyperbolic Thur manifold, or homeomorphic to a surface times R. Right. So we get this compactification of weakly almost Fuchsian space. And then a corollary of that is that if we have any if the maximum principal curvature of some minimal surface in like our hyperbolic manifold M of topological type of surface times R, if the maximum principal curvature of any minimal surface in that is less than or equal to 1, right? So if lambda naught here is less than or equal to 1, then we're able to get uniform upper bounds on volume of the convex core and on the Hausdorff dimension. So the Hausdorff dimension is the most 2, and so we're able to say it's like less than 2 minus epsilon. Uniform over all manifolds in weakly almost Fuchsian space. Right. And so we're able to, even though like this kind of direct approach of trying to estimate volume of the convex core and Hausdorff dimension of the limit set in terms of the principal curvatures, it doesn't work as lambda naught goes to 1. we are able to, by this compactness argument, by this kind of soft argument, we're able to get some upper bound just in terms of the maximum principal curvature of the minimal surface in the middle. Right. And so, I mean, all that's happening here, basically, once we've constructed the compactification is the fact that volume of the convex core is just a continuous function on weakly almost Fuchsian space and extends to a continuous function on the compactification. And then we're just using, a continuous function on a convex space is bounded. So that's kind of, what's going into that. So yeah, that's the one of the main corollaries that comes out of our compactification that we construct. And then another is so this theorem which says that there exists a universal epsilon only depending on the genus of the surface, which I'll say what that is in a second, which surface, but so that so we just have G is the genus of the fiber for a closed hyperbolic manifold that fibers over the circle. And so the statement is that there's this universal epsilon, so that for any closed hyperbolic manifold that fibers over the circle with fiber a surface of genus G, every minimal surface isotopic to the fiber has to have principal curvature bigger than 1 plus epsilon at some point. Right. So there's so we kind of already know, if we have a closed hyperbolic manifold that fibers over the circle, if we're handed one, we know that it can't have a minimal surface isotopic to the fiber with principal curvatures less than or equal to 1 everywhere by the theorem that I just said, where if you have a closed hyperbolic manifold with minimal surface with principal curvatures less than or equal to 1, that's essential. You can just sort of pass to the cover corresponding to that surface, right? So if we just sort of, in this case, if we pass to the cover corresponding to the fiber by unwinding along the base, then we'll get this closed hyperbolic manifold that is topological type of surface genus G times R. And then this theorem about weakly almost Fuchsian manifolds being QuasiFuchsian is going to tell us that we actually have to be QuasiFuchsian, but we know that the limit set of the cover corresponding to the fiber of for just closed hyperbolic manifold that fibers over the circle, it has to be the whole sphere of infinity. So we know it can't be QuasiFuchsian. So what I'm saying is, off the bat, we kind of know that there has to be for any given closed hyperbolic manifold that fibers over the circle fiber surface of genus G, we know there's some epsilon, so that any minimal surface isotopic to the fiber has to have principal curvature bigger than 1 plus epsilon. But what isn't obvious from that is that there's some epsilon that works for every closed hyperbolic manifold that fibers over the circle with fiber a surface of genus G. And so kind of using our compactification and a soft argument, we're able to show that there's some kind of gap here where for any closed hyperbolic manifold, any minimal surface isotopic to the fiber, if the fiber is genus G, then there's some universal epsilon that just depends on G, so that the principal curvature is larger than 1 plus epsilon at some point. Right. And so, we can always just minimize area and kind of the homotopy class of the fiber to get, some, and turns out you can take it to be an isotopy class of the fiber. So, there's always some minimal surface that's isotopic to the fiber just by general existence results for minimal surfaces. And so this is just, giving a universal lower bound on what its maximum principal curvature is, just depending on the genus of the fiber. And so this improves a theorem that Breslin proved, which is basically the same theorem as this, but with he also assumed a lower bound on the injectivity radius. And so and so kind of with our compactification, which extends the Deligne-Mumford compactification, we're able to kind of deal with if the injectivity radius is getting small and we're sort of forming cusps, I guess, where we're able to kind of basically have something analogous to the leading moment for compactification, so that we're able to handle the possibility that the injectivity radius is getting smaller and smaller, and the compactness arguments that we want to do. Right. Cool. And so, one question that means you don't know how to do is whether this epsilon from the theorem, whether it can be taken independent of the genus. And so it probably can, but yeah, we don't know how to show that. I guess in hyperbolic geometry of surfaces, there are lots of theorems like this where, for example, I don't know, like the curve complex is delta hyperbolic. For any surface of any genus, and the delta for which is delta hyperbolic can be taken independent of genus. And so, so I guess we would expect there to be kind of a uniform epsilon you can take, but we don't know how to do this with kind of our methods. And I guess I would say there's just kind of broader question of how to what extent you can understand QuasiFuchsian space with just by kind of looking at minimal surfaces in QuasiFuchsian manifolds. And so right, and so just to kind of summarize, like if there's a minimal surface with small principal curvatures, then Karen Lundbeck says you can sort of recover the whole hyperbolic structure from that, and there's this really nice description. And then for what me and Zeno did, we were able to kind of like go to the boundary of what Karen Lundbeck did, and say that kind of a similar picture. That you have like a similar picture there. But in general, for QuasiFuchsian space, Zeno, Wang, and Ba-Wang have constructed examples where QuasiFuchsian manifolds that have arbitrarily many minimal surfaces in the middle. And so, in general, certainly you won't have this unique minimal surface. And so, so kind of the question is like, to what extent you can recover the geometry from these minimal surfaces in the interior, like in the convex core. And right, so I guess I'll end my talk there. But thanks for listening to my talk, and cool.